Okay, today I want to finish up section 1.5 that we've been working on, which has to do with inverse functions and inverse relationships. And kind of as an add-on to this section, we have this topic of parametric equations. Parametric equations come from the word parameter. If you think about parameters as we use that phrase in like day-to-day language, it's kind of like the things that are maybe constraints or concerns in what we're talking about. If you're talking about the stock market, for example, going up or down, there are almost infinitely many parameters that involve that, businesses all over the world, and individual spending habits and all kinds of things that go into that. But for something simple, in a very physical representation, maybe something like the path of an object as it's flying through the air, or a ball, or a projectile of some sort, you could think of essentially there being a couple of things involved. If we're talking about the path of an object moving, maybe it goes up and down, goes up and goes over and comes down like that, or maybe something that's falling and it's moving out as it's falling, get some kind of motion like that involved. You could think of motion, say, something like this, as consisting of sort of two different kinds of motion. Motion that's left and right, and motion that's up and down. As you can see, if you start here and you go down to the right, you're going both down and you're going both to the right. So if we were interested in mapping that progress, for example, in the x and y direction, and in the x direction, either left or right, and in the y direction, either up or down, kind of independently, looking at the horizontal motion and the vertical motion separately. What would be interesting is if we had something that would predict the position left and right, and another equation that would predict the position up and down. Well, that's one of the ways that parametric equations can get used. A parameter is, again, something that affects something else, or a quantity that might be dependent upon in order to determine some other quantity. So what we're going to think about here is a parameter being time. In other words, as this dot moves down and to the right, time is changing. Okay, so we start at t equals 0, t 1001, 1002, 1003, 3 seconds pass, and that object moves both to the right and downward. And if we were curious about the position in the x direction, we might have one equation. For example, the position depending on time would be 15 times whatever the time is. So I just made this equation up. But that would mean something like something that's traveling horizontally at a speed of 15, say, feet per second. After 1 second, the x position would be 15. After 2 seconds, it would be 30. After 3 seconds, it would be 45. And you might think of something just moving along like that, and you could predict that the position horizontally at any given time. However, what if the thing is not only moving sideways, but it's also moving down? So maybe as it's moving to the side, it's also moving down. That vertical motion in the y direction would be predicted by some other equation. I've got one here, negative 16t squared plus 6. The negative would be because we're going downwards, and that's going to give us a negative position. And so we could say, okay, at time equals 1 in this scenario, at t equals 1, we could predict then the x position at time equals 1 would be 15 times 1, which of course is just 15. And the y position at t equals 1 would be y of 1, which would be negative 16 times 1 squared plus 6, which is going to be what? Negative 10. So that would tell us, according to this model, that after 1 second, our object had gone 15 feet to the right because the x position is 15, and 10 feet down. So it might be somewhere down here if this was our origin up here. So that's kind of how this can go. You can get that motion in two directions given by a set of what are called parametric equations. So time is the parameter that both the x position and the y position depend on. This is all somewhat contrary to what we've done prior to this, where we've always had y or f of x dependent on x. So the question might come up, would it be possible to, because x is related to time and y is related to time, could we find a relationship directly between y and x, kind of no pun intended, but taking t out of the equation, taking time out of the equation. And so could we develop a function that relates the horizontal position directly to the vertical position? So in other words, what if we wanted to know what the height was when the horizontal position was 30 feet? Well, there's a couple ways we could do that. We could find out when is the x position going to be 30 feet. You'd set x of t equal to 30, divide both sides by 15, you get t equals 2. So it's going to be at a position of 30 feet horizontally when t equals 2, and then go plug 2 into this equation, negative 16 times 2 squared plus 6, and get a y value for that, and that would tell you what the height is going to be. But that was kind of indirect. We had to find t based on an x, and then get that t and plug it in here. What I'm talking about is maybe going directly to a y value from a given x value. So what we can do is recognize that our first equation, x basically is equal to 15t, and we have a second equation, y is equal to negative 16t squared plus 6. What we can do is use this first equation and realize that t would be x over 15, right? Just rearranging that equation to solve for t, and then use that fact in the y equation. And we would get negative 16 times x over 15 quantity squared plus 6. So that would be negative 16 times x squared over 225 plus 6. So I'm not going to worry about trying to reduce this fraction. It's not going to reduce. So negative 16 squared, negative 16x squared over 225 plus 6. So this establishes a relationship directly between y and x. So that's a fairly straightforward use of substitution that you could almost think back to your Algebra 1 days. That would give you a direct relationship between y and x. So there you go. So that's about as much as we're going to do with parametric equations is recognize that there are such things, that you can have x and y and z for that matter, and a whole bunch of other things, all depending on time. And from those, can you get a relationship that's directly y in terms of x? Having said that, you'd want to respect the fact that your calculator can also handle parametric equations. A lot of things the TI does that we haven't even learned yet, and this is one of them. So I want to emphasize the fact that we can look at our calculator. I have a picture of it up here. And if you just went from a blank screen and hit mode, if you hit the mode key, this screen will come up. And if you scroll down your screen, if you look down your screen, chances are your fourth line down, that function line right there will be highlighted. Well, if you scroll down to that and then go over one spot over and hit the enter key, you will then be in parametric mode. And what that allows you to do is write equations such as they are right here, where x is a function of time and y is a function of time. So I gave you an example of what that screen would look like. You press y equals, and instead of having just y equals a whole bunch of different times, you now have x in terms of t equals and y in terms of t equals. So each equation, the blue equation, the red equation, the black equation, the purple equation, they have a spot for x and y both in terms of t. Notice the key where we normally hit our variable. I just put in 15 and then I hit the variable key right here. Notice that the variable key has x, comma t, comma theta, comma n. Well, those four different variables relate to these four different modes that the calculator can be in. When we're in regular function mode, your variable over here is going to be x, and it will default to that. When you're in parametric mode, your variable is the second one, the t. And that's because most oftentimes the parameter is going to be time. These other two, we're not going to dabble with much in this class. We will dip into polar a little bit. That's another mode that we can look at. And in polar equations, we're talking about angles that are changing, so the variable becomes theta. And lastly, in sequential mode, when we're looking at sequences and series, the thing that we're concerned about there is what item we're looking at in a list of maybe n things, and so the variable goes to n. So there you go, you just learned a little bit more about that variable key and why it has all those other letters other than x on it. Anyway, once we have that in y equals, we should be able to graph this thing. So I hit graph on this guy, and this is what showed up. This is a standard window, and you can see it kind of looks like half a parabola, which kind of makes sense, because if you think we have this relationship here between y and x, we have negative 16x squared over 225 plus 6. That's a classic parabola that has that opens downward. In other words, it's got that negative out in front of it, which is going to mean that it has kind of an upper bound rather than a lower bound. But you say, well, what the heck? What's going on? Why isn't it showing us maybe the other part of this? And so if you hit the window key, what will come up is a window that looks very different than your, well, not very different, but a little bit different from your window when you're in regular function mode. Because the first option up here is your T-min and T-max and T-step. And what that is telling you what what time values are being plugged into this thing. And it kind of defaults to a T-min of 0, because if you think of time being what T is representing, having a negative time value really doesn't make a whole lot of sense, because you can't go back in time. But if you start at T equals 0 and then go on to, again, the default mode is 6.28, which you might recognize as 2 pi. A lot of things we're going to find out later in the year kind of have a periodic nature to them that's going to have to do with the way, well, trust me, we're going to get to that later this year. But you get a T-min and a T-max and a T-step, which is telling you kind of how often is it checking in and plugging in a new T value into these relationships up here, 15T and negative 16T squared plus 6. Now, you can mess with these. You can change T to have a negative value. As a min, you could go like negative 5 to 5. You can change your T-step to be, 0.1 if you want, 0.01, whatever you want. The smaller that T-step is, the slower the thing will graph, because it's making a whole bunch more computations then. And of course, your X and Y values are there kind of as normal. So because it's never letting T get below 0, that's why you're in this relationship. 15 times 0, of course, is 0. 15 times 1 is 15. So you're going to get those kind of X values that way. And you can get your Y values by plugging those T values in here. So that's kind of what's going on with that stuff. You're really seeing an X relationship and a Y relationship. You're not really seeing a T axis here. T is just kind of going on in the background to let you know what's going on. So there you go. That's an introduction to parametric equations, how they work, how they can be graphed. Again, not terribly important right now. This stuff will show up again usually in Calc 2. So you may not ever see it again unless you get to BC here at Slasianum. But it's a good thing to just kind of have some exposure to, and it will help you in your study of physics as well. So there's parametric equations in a nutshell.